Our Bowie lecturer today, Jeff Freymueller, received his PhD at the University of South Carolina in 1991. I think it was an exciting time to be a graduate student. It was the time where GPS was first starting to be used for deformational geophysical problems. And Jeff took this a bit further than many, and he actually delved deep into the geodetic part of the problem. He actually was a member of the technical staff at the Jet Propulsion Lab while he was a graduate student. And at the time there, they were developing GPSy and the techniques to use to process GPS data. And Jeff actually has some pieces of that that are well known among GPSy lore masters. After Jeff did a postdoc at Stanford, he moved to the Geophysical Institute at the University of Alaska at Fairbanks. Now, me not knowing much about Alaska, admittedly, I guess I assumed that Jeff would just sort of disappear, in spite of his height. But he did not disappear. He actually published, began publishing almost immediately, many highly cited papers on a range of geodesy and geophysics, including one classic paper, highly cited, on plate motions from GPS. He began then to start to explore the range, the full breadth of geophysics in Alaska, including tectonics, volcanism, sea level, viscoelastic and elastic adjustment. More recently, he played a crucial role during the planning of the EarthScope program. He did this by continually asserting that Alaska was indeed a part of the United States. And once we verified this, it was fully accepted and is now a major part of the EarthScope program. And I think really that the community owes Jeff a debt of gratitude for this, for his steadfastness. I should also mention that he's served as Geodesy Section President and also in many other roles of community service, both within AGU and in other societies. And because of his long record of really excellent research, we invited him to give the Bowie lecture tonight, titled Geodetic Constraints on the Tectonics of Alaska and the North Pacific.
Okay, thank you, Jim. So I guess if you owe me a debt, you've probably paid it off by actually coming to my Bowie lecture. So I'll let you enjoy for a moment the view of Denali. This is the highest point in North America. And actually, this is one of our field locations. A typical view of students in Alaska doing field work, just the ordinary stuff that they do all the time. Anyway, what I did want to do here is thank and acknowledge some of the students and postdocs and key collaborators who I've worked with on Alaska tectonics. And this isn't everybody that I've worked with, but this is the people I've worked with on Alaska tectonics specifically. And I'll start with the students and postdocs: Hilary Fletcher, Dor Taman, Chris Larson, Chris Zweck, Sigrun Hreinsdottir, Hisashi Suito, Shamik Sil, Tom Fournier, Yusaku Ota, Julie Elliott, and Ryan Cross. And there's some other students who haven't published things yet, whose names aren't yet on the list. And some key collaborators, Steve Cohen, now retired from Goddard Space Flight Center, who really got me into looking at post-seismic deformation. Misha Kogan, who I've been working with recently on sort of cross Alaska-Russia, crossing the boundary work. John Bevan and Gene Sauber. Okay, so having been in Alaska for about 15 years, I can't resist. We have to remind you of the map scale. It's a really big place. And In many cases, people don't remember exactly what the scale bar should be on the maps. I've tried to put scale bars, but sometimes even when you put scale bars, they're not intuitively known like many other places are. But rather than just use this slide to sort of show the size of the state, here are a few key geographic locations that I'll have to mention at various times in the talk. So first of all, the Alaska Peninsula over here is this sort of long, thin peninsula that essentially extends into the Aleutian Island arc. And so its backbone is arc volcanoes of the Aleutian arc. Kodiak Island is this large island here. Whoops, didn't mean to do that. And then the Kenai Peninsula is this prominent peninsula here in southern Alaska with Cook Inlet on one side and Prince William Sound on the east side. And then finally, southeast Alaska here, which is not a peninsula, although it looks like it in this case, but Canada has been eliminated in this figure. All right, so, but I'm not going to eliminate Canada from the talk at all. I'm going to focus initially on Alaska, but then I wanted to say some things about some sort of bigger picture of tectonics around the North Pacific, essentially stretching from the northern Cordillera of Canada here through Alaska and into Northeast Asia. Okay, so Alaska, part of the big story for Alaska, of course, is earthquakes. It's a subduction zone. The Pacific plate here is moving roughly to the north. That orientation gets more westerly as you go to the west. And also the subduction about here is essentially trench normal. When you get out here, it's virtually trench parallel. So there is actually still a bathymetric trench, but it's almost like a strike-slip boundary in terms of its relative motion, or very close to one. And actually, the obliquity goes the opposite direction here. So the obliquity here would be in sort of this direction for subduction. So we have the subduction zone with the large earthquakes noted. The biggest of these is the 1964 Great Alaska earthquake, still by a small margin, the second largest earthquake recorded instrumentally. And its rupture zone is about 750 to 800 kilometers long and about 200 kilometers wide. So that's what it takes to get up to the 9.2. Then you can see the strike-slip boundary in here on the southeast part. And there's a fairly complex transition in between the two. I wanted to call one more earthquake to your attention. This is the 2002 Denali Fault earthquake, which is a fascinating event, and all sorts of interesting opportunities resulted from this. From a geodetic point of view, it actually caused a number of problems because it displaced sites up to a fairly large distance away from the earthquake. And so when I talk about tectonics, I can only use data before the earthquake for an area that surrounds this rupture. Otherwise, the post-seismic deformation from the earthquake is simply too large. And I'm not going to give you too many details about the Denali Fault, although I'll mention it a little bit. I do have a talk tomorrow on Denali post-seismic deformation. Before I forget, one more thing. In that transition zone from the subduction zone to the transformer strike-slip boundary is a chunk here of crust called the Yakutat block or Yakutat terrain. This appears to be, geologically speaking, something like an oceanic plateau in terms of its material, and it is in the process of colliding with North America. So this Yakutat block now moves independently from both Pacific and North America. This is just a map of about a year's worth of seismicity from the earthquake catalog. There's 27,000 earthquakes in the catalog. The important ones for here are the blue events, which are the shallow crustal events. And in addition to seeing all sorts of events along the plate boundary in the south, you actually see a whole host of earthquakes that extend quite a distance up to the Arctic coast over here. There's a band here in Canada. This is the Mackenzie and Richardson Mountains, and then also earthquakes in northwest Alaska. Some of the areas where there are no earthquakes on this map might actually have earthquakes. They simply are not monitored, so we don't know whether they do or not. And some of these events up in here, for example, are in the magnitude 4 range. So there have been quite a few, tens of magnitude 3.5 to 4.5 or so earthquakes in the last couple of years in this region. So the impact of the subduction and other processes affecting southern Alaska extend a large distance inland. All right, so I'm going to say a little bit about the GPS measurements that we've made and what we have from that, and then I'll go through an example of using the GPS velocities and trying to untangle multiple sources of deformation that contribute to the GPS velocities. It'd be very nice if we could just say that one thing explains what's happening in a particular area, but it's really not that way at all. I'm going to talk about, actually in opposite order to what's listed here, because I forgot to change the outline after I moved things around in the talk. I'll actually talk about southern Alaska, or I'll talk about southeast Alaska, rigid Bering plate, general block configuration of southern Alaska, and the mobile northern Cordilleran margin, and East Asia across the branch cut. In this case, refers to the branch cut in the map. We typically break our maps in particular places which don't reflect tectonics, but reflect politics or other reasons. Okay, so Alaska GPS data. Alaska is a place where if you want data, for the most part, you had to go out and collect it into the field. Most of what I'm going to show you is based on campaign GPS measurements. So the sort of measurements that you saw in the background of the photo there, where somebody goes out and sets up a GPS receiver over a marker for a few days or a few weeks and eventually recovers it with the data. There were some early surveys done by the National Geodetic Survey, but things really started in earnest in the early 1990s. There were three significant NASA-funded projects under their Dynamics of the Solid Earth program, working from west to east. John Bevan, Jim Savage, and Gene Sauber had big projects. I wasn't involved in those projects yet, although I did have the right first initial to be involved. But I got involved in some of that later and ultimately was able to incorporate all of that data in the work that I did. The first work on the Kenai Peninsula was actually started by Steve Cohen from Goddard in 1993, and the goal was really to start looking at post-seismic deformation, and I got involved in that project very fortunately right when I started in Alaska in 1995. And I should also thank Max Weiss for this. He was sort of the matchmaker who put Steve Cohen and I together on working on this problem, and it was really an incredibly successful collaboration. Some early work was done in the Aleutians by John Oldau and Hans Ave Laumont, starting in 1996, that provided some of the critical data from the western and central Aleutians. And then essentially the work that I did and my group has done in Alaska started in 1995. I just wanted to call out a couple of other groups at my institute. The Alaska Volcano Observatory, there's quite a bit of work that we did to measure and monitor volcano deformation, and also the Alaska Earthquake Information Center, who operate the Alaska Seismic Network. There were many, many opportunistic field measurements that we got by simply sending a receiver with a technician from the Seismic Network who was going somewhere and could set it up for a few days. Thanks, Steve. I see you over there. All right, so putting together all of this with the actual regularly funded projects, we developed a velocity field for Alaska based on a pretty large number of sites. This is based on a compilation that it was published about a year ago. And so in this figure, the red dots, or the red diamonds, are campaign GPS sites, and the blue dots are continuous GPS sites that predated the EarthScope Plate Boundary Observatory. Most of those continuous sites were actually not set up for tectonics or crustal dynamics or geodesy. They were set up for surveyors, basically, but that's the data we had. You can also see some white dots. Those are Plate Boundary Observatory sites. I actually plotted those on the figure first, so you don't see them where they're covered, where there's a dense campaign data. And I did that in order to emphasize the places where the Plate Boundary Observatory is going to provide totally new information about tectonics, because in the places we already had dense campaign data, the steady velocities from PBO are only a modest increment to what we get from the campaign data. On the other hand, the PBO data let us look at time dependence and transients that we could not do with the campaign data. And earlier today, there were a couple of talks, one by Misha Kogan talking about Chukotka, and one by Julie Elliott talking about Southeast Alaska and the collision here that provided a lot of detail there. I'll show a little, just one figure relevant to this one, and not really anything for this one. Okay, so what we have in Alaska is a superposition of multiple sources of deformation. So a GPS velocity is really the result of a superposition of several things. First is, of course, long-term tectonic deformation, and by this I'm really referring to sort of the rigid block or plate-like motion For example, in the case of motion of the major plates, it's the plate motion. There are also earthquake displacements and transient slow slip that are, of course, significant. We also measure, included in the velocity estimate is elastic deformation associated with faults that are locked. That is, faults that are not slipping freely all the way to the surface, but have a portion of them that are stuck. This is essentially your earthquake cycle deformation. Also post-seismic transient deformation, glacial isostatic adjustment, and in some cases deformation of active volcanoes. In this particular talk, I'll be focusing mostly on the ones that are in bold, and I'll make some brief mentions of some of the others, but that's all. Some of these effects can be separated easily from the others, and some cannot. And in some places, some are important in places and not. So, for example, deformation of active volcanoes is not an important problem when you move away from the Aleutian Arc. But in general, we often have to deal with a combination of effects. And that's perhaps best illustrated by looking at the rupture zone of the 1964 earthquake. So the red outline here is the rupture zone of the earthquake as defined sort of traditionally from aftershocks. The scale here is 250 kilometers on the little scale bar down there. The red arrow next to the scale bar is approximately to scale the Pacific plate motion relative to North America, and the green vectors are GPS velocities relative to North America. So as I mentioned, when you go near the Denali Fault, these velocities are based only on pre-earthquake data, pre-2002. When you go farther away, we corrected for the displacement from the earthquake. So we used a model or a direct estimation of the offset due to the earthquake, and then estimated velocities. So you can see a fairly complex pattern. The first thing that probably stands out are these very, very large vectors here, which are moving essentially in the direction of plate motion. Over a little bit to the west, you see, in fact, sites that are moving back towards the trench, almost in the opposite direction of plate motion. And again, this is relative to the North American plate. So we would expect, if you try to explain these with tectonics, it would require essentially seafloor spreading type rates somewhere in western Alaska. Up here is the Denali Fault, and you really can't see at this scale what's going on. I will show you a blow-up of this in a few slides. But there is right lateral shear visible across here as well. Couple points about these large vectors, as we'll see, result from elastic deformation from the locked subduction zone. And there has to be a pretty large gradient along strike in that, because if you take a position relative to the trench, like here, for example, and you look at here and you move up into Prince William Sound, and neither of these are working very well, but if you move up into Prince William Sound, these vectors are substantially larger than the ones over here. And if you sort of follow the same distance from the trench, you get vectors that go to zero and eventually go back. So there has to be an enormous gradient in that elastic signal along strike. And finally, one last thing to mention here is this little inset shows two orientations, not particularly to scale. This is the Pacific direction, essentially this. This is the direction of the Yakutat block as determined from data further off the screen. And over here, these vectors are parallel to the Pacific direction, but these are essentially parallel to this Yakutat direction, which is rotated about 20 degrees from Pacific. All right, so the primary contributions to this velocity field come from two effects. The first is post-seismic deformation from the 1964 earthquake, and the second is the slip deficit from the locked subduction zone. And I say variable because, of course, it's variable along strike. Now, the right figure has the color coding is what you can see. There are some contour lines, which I really doubt you can see. But the bright red colors indicate a slip deficit of essentially 100% of plate motion. That is, the fault from the surface down to a significant depth is stuck and not moving. And so when the fault is not moving, we have a slip deficit relative to its long-term rate. So we have a big region here that is stuck, a region in the middle of the 1964 earthquake zone that is apparently dominantly slipping. These yellow colors are about 50%. And then when you get a bit farther down dip here, you get to an area where there's essentially no slip deficit at all. And I'll show that in a few slides later on after I finish this particular example. So the elastic effect is, from this locked subduction zone, depends on essentially the width of the region of the fault that's locked. And this particular figure, the scale on the x-axis is actually 200 kilometers per division. So it's a very large scale sort of figure. And there's some, I guess, y-axis exaggeration, I should say, I suppose to be the way to put it. But what you see on the left-hand side is a relatively smaller patch, not as wide, a patch that is stuck, and on the right-hand side, a patch that is stuck for a larger distance. And if you compare the velocities at any particular point, for example, along this line, you can see that the effect of this smaller lock patch produces a smaller deformation on the overriding plate than the larger lock patch does. And so fundamentally, it's this relationship between the area that's locked and the area that is and how far that extends. This relationship with the deformation is what allows us to figure out what that deformation, or that slip deficit rather, is on the plate interface. And then finally, in this case, there's a zone in the middle that is creeping. So there's no locked zone here, and the deformation gets very, very small in that case. So here's our data again. And so the first thing I'm going to do is I'm going to subtract out the best available model that we have for the elastic component. And this comes from a paper that was recently published in JGR by Suito and Freymueller. So here's the vectors, the data, and here's what we get when we subtract out the elastic component. So if you just look at that, you can see all of that motion in the trenchward direction, or sorry, in the direction of plate motion is being removed by the elastic correction. And what's left then is that trench towards the trench motion extends almost along the entire length of the rupture. So if you look beforehand, you could see the trenchward motion here, but it was kind of hard to see here. After taking out the elastic effect, you see that it extends over the whole region. If we compare that now to a model of viscoelastic model for post-seismic deformation following the 1964 earthquake, also from the same source, those are the red vectors. And so, as you can see, those are quite similar in both cases. So now let's subtract off those red vectors, and we're left with residuals. All of these are on the same scale, by the way. Now, these residuals are actually pretty large. In fact, if you look on the Kenai Peninsula here to Kodiak, there's a pretty systematic trench parallel residual that you can see in the residuals here. And if you look up by the Denali Fault, there's sort of a rotational systematic residual up there. So let's first look at the Denali Fault case. So there's some small red vectors there, which I'll blow up. Actually, I'll blow up in 2 slides. So there's some small red vectors that I'll blow up in a couple of slides that are from a Southern Alaska block rotation model that my student Hilary Fletcher proposed back in 2002. And the idea behind that model is that Southern Alaska, south of the Denali Fault and the Tachinda Fault here, is rotating about a pole of rotation that's located nearby, just offshore here. And that pole of rotation is essentially the small circle, the pole of the small circle formed by the faults. So let's take a little bit closer look at the Denali Fault so we can see where that particular model comes from. So on the left-hand side are the original, this is the raw data relative to North America for the area around the Denali Fault. And you can see there's a general trenchward motion. Even back here, which is the Fairbanks area, which is about maybe 800 kilometers or so from the trench, we still see this here, this trenchward motion of about 2 to 3 millimeters per year. And so if we want to look across the Denali Fault, the easiest way to see what's happening on the Denali Fault is to take velocities relative to some local site. So on the right, you see velocity vectors relative to a site right in here called Garner, which is a continuous GPS site that we set up back in 1997. And that's the dot right there. And when you look at these relative velocities relative to a local source, most of what you see is now fault parallel. And in fact, the total across this whole zone is about 8 millimeters per year of right lateral motion. So if you're standing on this side, the other side moves to the right. And by the time you get out to the southernmost sites, you're looking at about 8 millimeters per year. The other thing we can look at for the Denali Fault is a profile which runs along here, along one of the other roads that crosses the fault. There's not as much data from that profile, but here it is. So the top figure shows the fault parallel velocity along that profile. So this is the south side and the north side, and the red curve is a simple elastic, just a two-dimensional elastic half-space model with a slip rate of about 6 millimeters per year, which actually fits the data quite well. Interesting that on the bottom is the vertical velocity, and actually there's a systematic vertical offset that's associated perhaps with the fault or perhaps with the Alaska Range. It's actually at this point not fully explained. Some of this can be explained by glacial isostatic adjustment, but not all of it. And so that's still something of a mystery. I don't know whether this actually relates to the Denali Fault or whether it's a combination of some other loading effects. In any case, in both cases, at this particular crossing, we get about 6 millimeters per year. At the other one to the west, we get about 8 millimeters per year. This is similar to the paleoseismic rates that are determined from the western end of the Denali Fault. However, at this location on the Richardson Highway, the paleoseismic rates seem to be higher, actually significantly higher, almost double what we see in the geodetic rates. We simply don't see the strain associated with those, that sort of a paleoseismic rate. So that's a problem that is still to be resolved and may take quite a while because the earthquake has caused all sorts of chaos to break loose from the point of view of doing geodesy. All right, so here again is the Southern Alaska block rotation model, and what if we, oops, this is blown up a little bit, so you can see the scale is now changed to make it easier to see the vectors, and essentially this model predicts everything certainly within 100 or 150 kilometers of the Denali Fault to the south is predicted fairly well. And actually some of the sites further away are predicted fairly well as well. Essentially along the whole thing, the fault parallel component of the velocity is explained fairly well. Although in this case, there's still some residual here that's fault normal. The other thing to notice here is that for the most part, except in this area right here, if you're in the northern part of this figure, the block rotation model fits fairly well. In here, there's some complications because I mentioned transient slip. We had a very large slow slip event that lasted about 3 years from 1998 to 2001. And the velocity field that I'm showing here actually averages across that event. So there is some time dependence that's not properly taken out of the velocity field. And that accounts for some of the misfit, for example, in the case of these sites. But if you would say that north of here, the block rotation model fits fairly well, but south of here, it clearly fits very poorly. So down on the Kenai Peninsula, there's a substantial trench parallel residual that's much, much faster than what would be predicted by that block rotation model. And this may reflect the motion of a sliver, of yet another block or sliver in a trench parallel sense. The typical residual here is about 5 millimeters per year. So remember that number. And remember 5 millimeters per year trench parallel because you'll see it pretty soon in a nearby place. So again, here's our data, and after having taken all of these models out, we still have some things to explain. We need to explain how this is moving, and we can do pretty well up here, but we need to improve the model for this. All right, so some caveats and some lessons. First of all, these models are not independent. And I peeled off these elements one by one because it makes a nice story. And it shows pretty clearly, I think, how these components affect the velocities. But that's not actually the order we estimated them. So what we actually had to do is we had the block rotation model already from previous work constrained by the Denali Fault, the GPS across the Denali Fault. So we removed the block rotation model. Then we did a whole series of viscoelastic post-seismic models, each with a different viscosity for the mantle. And then for every viscoelastic model, we subtracted that and then estimated the best elastic model, essentially the elastic plate coupling model for that. So what we call the best elastic model depends on the viscoelastic model that you choose. If if we had a different viscosity, we would get a different elastic coupling model. Now, certain features don't change. The fact that you've got these big along strike variations, they don't change at all. But the detailed shape and the width of the locked zone does change when you change the post-seismic model. So these models are pretty strongly coupled. Both of these may depend, at least in detail, on the model for deformation of the overriding plate. And as you can see from the residuals, we need to actually improve that. That's some work that's in progress right now. We'll be reevaluating both the best elastic and viscoelastic models with some better upper plate models and doing a more complete joint inversion. And again, what this trade-off means is that the components that are in the direction of plate motion, those are poorly constrained because the models trade off very strongly in that direction. But for example, the trench parallel direction is pretty well constrained because the elastic model doesn't produce trench parallel motion and the viscoelastic model doesn't produce trench parallel motion. So it doesn't matter which one you use, you still have that trench parallel component, and that has to be something that's tectonics of the upper plate. All right, so let's move to the southeast here. This is just a preliminary velocity field estimated for that transitional region. So over here is Prince William Sound, and the 1964 earthquake went to somewhere over here. We don't know exactly how far. Down here is this transform boundary starts over here at the edge of the page. So what I wanted to show here is that if you look at the northern part, there's a dramatic difference between these over here and these velocities over here. These are pretty close to that southern Alaska block rotation model, and these are not. And probably what that means is that the plate interface, the lock zone on the plate interface from the 1964 earthquake asperity probably extends somewhere out to about here. And actually in the elastic model that we've done so far, our plate interface itself didn't actually extend that far. So again, there's things that need to be improved in each one of these models that we try to remove. Okay, so in Southeast Alaska, actually the biggest story is glacial isostatic adjustment. And there's been enormous amounts of ice lost from the ice fields and glaciers since the end of the Little Ice Age. In particular, the Glacier Bay, which is right in the middle of this little bullseye down here, deglaciated over about 1800 to 1900, and the melting of the ice was equivalent to about 8 millimeters of sea level rise just from that one glacier system. So actually, this whole region, including the glaciated areas up here and a little farther down, actually over the 20th century probably put more ice or more water into the ocean than Greenland and Antarctica combined. So this is a major source for sea level rise. But we know the load history well, because a lot of glaciology work has been done here. We have a pretty good idea of the load history. So if we know the load history, we can find an Earth model that fits the vertical, observed vertical velocities. And these contours show the contours of uplift rate. The peaks are over 30 millimeters per year. And this agrees with the peaks in the data, one down here at Glacier Bay and one up here. So this is a combination of viscoelastic response to post-Little Ice Age, where we need to have a very low viscosity asthenosphere to explain this, and also to the present-day melting, which has accelerated in the last decade or so. The green vectors are the horizontal predictions that come with the model, and those actually have a significant impact on looking at the tectonic problems. So this is a figure that Julie Elliott actually showed earlier today. This is on the left is the data, on the right is a block model for Southeast Alaska. So this is an elastic block model. Each one of these colored regions is on the right-hand side is assumed to be a rigid block that rotates about some polar rotation. The block boundaries are faults. The slip rates on the faults and sense of slip depend on the relative block motions on either side. And we account for the elastic deformation associated with the faults as well as the fault motion. I don't want to go into too much of the details here, but here's the Yakutat block. It moves about 50 millimeters per year relative to North America. And there's about 46 millimeters per year of contraction going on between the leading edge of the Yakutat block and southern Alaska. And the effects of deformation actually extend a considerable distance into the continent. So this is between the Fairweather and Denali faults. strike-slip faults, we actually find a need for two independent blocks, both of which have significant motion. These solid vectors refer to this scale, whereas the white vectors refer to the larger scale. And you can see this rotational motion associated with the leading edge of the Yakutat collision, and that actually produces rotational motion in this northern Cordillera, which is reflected in all of the data up here from the northern Cordillera. Okay, we can look at that on a larger scale. This is a figure that comes from Stefan Mazzotti, and he did some GPS work down at the Queen Charlotte Islands, which are down right in here in Canada. And what he found in this case, the Pacific plate, although it largely moves margin parallel, at the Queen Charlotte Islands there's actually almost 2 centimeters per year of contraction, along with the strike-slip motion. So it's a transpressional system. And what he found was that there had to be at the Queen Charlotte Islands significant deformation inboard of the islands themselves. That is, there had to be active faults on the inland side of the Queen Charlottes in here. And then here in Southeast Alaska, I just showed you the model. This rotational sense matches the sense of convergence out at the Mackenzie Mountains. And there's also some campaign GPS data done by our colleagues in Canada across here, which confirms significant shortening occurring out here. So we actually see the deformation, even in this nominally simple transform boundary, actually extends a substantial way into the continent and encompasses much of the northern Cordillera. On the left-hand side, you simply see the moment tensors, earthquake moment tensors. For earthquakes, the small ones are less than 5, the big ones are greater than 5. Okay. And so the various arrows show Stefan's interpretations of the senses of motion. The red arrows show the senses of contraction or shear. Okay, so I'm going to move then to the west to look at the Bering plate. This is a figure modified from Mackey et al. 1997, who proposed a counterclockwise rotating Bering plate, and their proposal was based on seismicity patterns observed in the Russian Far East and also in western Alaska. They proposed a pole of rotation for the Bering plate relative to North America up here in northern Chukotka. Now, traditionally, this whole area is often considered part of the North American plate, although there's a lot of argument about some different parts like the Sea of Okhotsk and so on. So let's take a look at some of the velocities. First of all, from western Alaska. Again, these are relative to North America, and the scale here is 5 millimeters per year. So we have data from Bering Sea Islands, St. Lawrence and St. Paul. We have data from the Nome area in the Seward Peninsula, and data from a few places in the western Bering Sea coast. Once you get in here, you start to see effects of the 1964 earthquake and other things. So we can really only look at this little strip here along the Bering Sea coast. The motions here are about 5 millimeters per year relative to North America. So that's not particularly fast as plates go, but it's quite significant and cannot be explained by these sites being on the North American plate. So these are clearly not on the North American plate. And the motion here, again, we'll remember this direction. If we go down to the Alaska Peninsula, so the St. Paul Island is it's about over here and somewhat off the screen. We can look at the velocities from this section of the Alaska Peninsula. So again, Pacific plate direction is this way. If we look in the northern part, we see a tremendous amount of contraction here. Again, that is an indication of a very wide locked region on the plate interface. Less contraction in the Shumagon Islands in here, which would indicate less contraction or less locked region on the plate interface. And finally, at the very end of the Alaska Peninsula and the beginning of the Aleutians, we see essentially trench parallel motion with no strain whatsoever. The best fitting strain tensor for this is essentially zero strain. These are essentially moving as a rigid block. In fact, the rate of these sites is about 5 millimeters per year, trench parallel, okay, which was what we saw farther up here in the residuals to the models in the 1964 rupture zone. And in fact, if you were to subtract, you can see these rotations in the vectors. If you subtract the average of these motions from everything on the page, all of these vectors rotate and line up almost exactly in the direction of Pacific North America relative motion. So what we see here is a superposition of a motion of the arc here relative to North America and strain from the plate interface. So conceptually, this orange vector is the motion of the arc, the blue is the observation, and the white here is the subduction strain component, which depends on where you are relative to the trench. And so we can estimate both the arc velocity and the subduction strain component. And the way we do that is we first of all have to set up a geometric model for the plate interface. And this is work from Cross and Freymueller 2008. We took the geometric model that another of my students, Tom Fournier, had developed. We then do a grid search over a range of candidate arc velocities, and for each one we estimate a plate coupling model. Then we take the best overall model for this, which turns out in this case to be about 4 millimeters per year to the southwest. And there are some numbers here which indicate essentially the coupling coefficient or slip deficit, a wide zone with, that's mostly locked in the north, and then a zone that's mostly creeping, eventually resulting in a zone that's, as far as we can tell, completely creeping. Okay, so we have data from the Bering Sea Islands, we have data from the Alaska Peninsula, we also have some data from a couple places in the Aleutians, and the question is, can you fit all these with are these part of a single rigid plate, or are these maybe multiple plates? It turns out you can fit them fairly well with a single rigid plate. This is the yellow is the prediction for the Bering plate based on the pole of Cross and Freymueller. The purple vectors are the data. Here in the Andrianoff Islands, the blue are the data, but the red is the arc velocity that we estimated. And you'll note that the error ellipse is strongly elongated in the direction of plate motion. And that's, again, one of these trade-off problems between the coupling model and the arc velocity. The yellow, again, is the prediction. And then finally, for the Alaska Peninsula, the red, again, is the estimated arc velocity, and the yellow is the prediction. So we actually can fit all of these by a single Bering plate model. Now, we've repeated this sort of modeling exercise over everywhere in the Aleutian Arc where we actually have data. And the purple blobs that you see on here are the areas where the plate interface, we infer the plate interface to be stuck, that is locked, and not creeping. So there's a significant slip deficit accumulating for the next great earthquake. The areas in yellow are the areas where, for example, here, and also within the 1964 rupture zone are areas where we infer the plate interface to be creeping and not building up significant strain for future earthquakes. Okay, so let's look at this tectonics of the overriding plate overall. And so the yellow vectors now are the predictions from the Bering plate pole. The green vectors are the predictions from the southern Alaska block rotation model. Okay, and so the dashed lines here indicate places where we really don't know where to put the boundary. We know over here that we don't see velocities consistent with Bering plate. But there's a huge gap in data where we just don't know where it is. And it could be almost anywhere. The other thing is that if we think back to the 1964 area model, the area south of that red line had a systematic residual of about 5 millimeters per year trench parallel. And if you look at the Bering plate prediction here, this yellow vector, that's about 5 millimeters per year trench parallel. So it's quite possible that this might actually lie on the Bering plate, or this may even be a sliver moving slightly relative to both the Bering plate and North America. That's still somewhat to be determined. And then the block boundaries shown on the right, I mentioned briefly with the work from Julie Elliott's work. Okay. So let's look at the bigger picture now of essentially the entire North Pacific. So we'll go back to Stefan's picture of the mobile northern Cordillera margin. So the take-home message here is that we know all through Southeast Alaska, down to about here, we can measure the motion relative to North America, and there's significant motion, and it extends a significant distance inland. We know at the Queen Charlotte Islands from Stefan's work that the same thing is true. In our model, we extended the northern Cordillera block essentially all the way south to Vancouver Island. We don't actually know where the boundary of that is. The pole of rotation of that block is actually located near Vancouver Island. That is the pole of rotation relative to North America. So you'd predict very small motions. When you have very small motions, it's very difficult to tell which side of the boundary you're on when the boundary doesn't have very much difference across it in that spot. So it's entirely possible that actually from all the way down in Cascadia, we may not actually be on stable North America for example, around Vancouver and so on, although that's generally assumed in most people's models. But certainly when we move from the northern end of Vancouver Island up, we have a mobile system that extends all the way up around, all the way through Alaska, and all the way into East Asia. So I showed this before with the Bering plate model. So we saw that there is clearly evidence for a moving Bering plate. The other point here is that we don't find anywhere in here evidence for sites that move as part of stable North America. There simply isn't any stable North America in this part. Misha Kogan showed earlier today that velocities in the eastern part of Chukotka actually can be fit with a single polar rotation with the velocities of the Bering Sea Islands. So where exactly these boundaries are is still something that is to be determined. But I think one thing that we can say with confidence is none of this here is North American plate. And it's not clear whether any part of Alaska is actually North American plate or not. So let's take a look at East Asia. This is mostly work from others. This is a couple of figures from Trey Apple and others, one of Roland Bergman's students. And so you can see on the left a series of blocks separated, essentially defined by seismicity. So an Amurian plate or block, essentially Korea and Manchuria. The Eurasian plate beyond Lake Baikal, I think this is unambiguous. Japan is, of course, very, very complex. South China down here, and the Okhotsk plate, which is a point of contention about whether it exists or not. Nevertheless, there is some seismicity, and there is evidence up in here actually for quaternary faulting. And so on the right are his estimates of both the poles of relative motion, which I won't really talk about too much, just the vectors. So he estimated, based on his block model, 3 millimeters per year of extension across the Baikal Rift, and he estimated significant contraction between Japan and the Japan Sea. This is actually quite consistent with the geology and earthquakes, and a significant contraction in southern Sakhalin and shear in Sakhalin Island. So what we see in Northeast Asia are actually a whole series of blocks of about this sort of size. So here we have, in this particular case, an Amurian plate. This is from Cornet Kramer's global strain rate map. The colored areas are places of significant strain. The white areas are essentially inferred to be rigid. Now, he doesn't have much data from Alaska in the model, so he doesn't have the Bering plate in there. But in fact, we have essentially a continuous deforming zone all the way from here, all the way up through Alaska, through Northeast Asia, and there's really no place between Vancouver Island and Tibet where you don't cross something that is tectonically active. The whole of the North Pacific is mobile. So East Asia is broken into several of these microplates or blocks. Again, they're, in the case of East Asia, largely thought to be driven by the collision of India with the Eurasian plate. Some of these proposed microplates are controversial. They may, in fact, in some cases be simply diffuse zones of deformation rather than rigid microplates. For some time, I think people have wondered how far into the Northeast Asia do the effects of the India-Eurasia collision extend. Well, I would argue that when you actually look at what's happening from the other side, you could make the same argument here. In the Arctic Ocean, we have spreading between the North American plate and the Eurasian plate. The pole of rotation is about here, and we have to have contraction occurring between the plates over here. So I think we have three drivers. We have the driver of India, we have the driver of India or of North America and Eurasia sort of crunching together in Northeast Asia, and then we have the Yakutat collision in Alaska, which actually seems to have some fairly far-reaching effects as well. All right, so this, I pretty much have mentioned all of this. This distributive deformation is pervasive. We see it all around the North Pacific with these three major tectonic drivers: India-Eurasia collision, North America and Eurasia convergence or collision, and the Pacific and Juan de Fuca plate subduction, along with this Yakutat terrain accretion. So here's a possible plate or block configuration, and this is, well, Some of these lines probably should be drawn in crayon or maybe in something erasable, I guess. In particular, Misha Kogan showed earlier today that this sort of boundary here may not be a boundary. In fact, the boundary might be somewhere out here. This, again, I showed you the arguments for and against the Okhotsk plate, exactly what the boundaries are. But the bottom line is that we have the whole area is basically broken into these fairly large chunks, which are all moving relative to each other and relative to the stable parts of the North American and the Eurasian plates on the other side. So in summary, we see this continental crust surrounding the entire North Pacific broken into small microplates and blocks, which we can infer from the GPS data and models for the GPS data. It's a combination of several drivers, and we need still a considerable amount of work to be done because some of the boundaries are very uncertain, some of the models need some additional work, and there's plenty of productive work for not just me, but hopefully many of you to do in Alaska and the North. Thank you.
We have time for a few questions, although people are beginning to filter in. Hard to see. Gene?
Okay, so the question was, the EarthScope Plate Boundary Observatory is providing many more GPS stations. There will be a seismic array component, so one of the things, so what will that do in terms of helping things? One of the things that will do is that will actually help us locate seismicity in places where we know there's deformation, and the trends in the microseismicity may actually help us define where some of these boundaries are. It will also give more information about crustal structure and so on that will be relevant to that, and as well as information about mantle anisotropy that may be combined with what we see in the crust to learn more about really the dynamics of how the system is driven.
Are there any other questions?
Okay.
Jeff, I'd like to present you with this certificate. You've done this several times yourself. The Geodesy section recognizes Jeff Freymueller as the 2009 Bowie Lecturer for Geodetic Constraints and the Tectonics of Alaska and the North Pacific. Thank you.
Great. Thanks, Jim. Thanks, Jim. And so now we turn it over to the cryosphere, I think.
That was really good.
So.